Alright, here goes nothing. Hey Cricket, thank you for coming. I can watch the whole stream but just wanted to cheer you on. Thank you very much. It's very nice to have some people to talk to for a couple seconds at least. So here we go, guess. So this is the current state. Green is done, white is not. The ones that I want to implement first are the easier ones, the ones that has not to do with stack. So that means roll and roar, which is let's watch the reference for roar. Rotate left. So this is like shifting, except the byte that is going out goes to the carry, and the value of the carry goes to the byte that is coming in, if I am not wrong. Move each of the bytes in either A or M one place to the left. Bit 0 is filled with the current value of the carry flag, while the odd 7-bit becomes the new carry flag value. So basically, imagine you have 9 bytes, paying the 9th bit the carry flag, and then you shift all to the left, and the one that was the last becomes the first. So let's do that. So this is rotate left, and we have a version for the register and a version for memory. So let's do that. Roll comes after push. So let's go to our NES CPU and let's find the push methods. Here we go, and we are going to do rotate left. So let's duplicate some line and clean it up. And this method is going to be called rotate left register, and it is going to take the register A as the argument, and no addressing mode. And the other version are going to rotate left memory address, and instead of a register we'll take memory. So we will take addressing mode. So let's duplicate a couple more. Let's see, we want for rotate 1, 2, 3, 4 versions of memory and 1 version of register. So let's move this to our dock and toggle distraction free mode and start filling in some data. So the opcode is named roll. First one takes 1 byte and 2 cycles. Second takes 2 bytes, 5 cycles. 2 bytes, 6 cycles. 3 bytes, 6 cycles, and 3 bytes, and 7 cycles. So the addressing modes are 0 page, 0x, absolute, and absolute x. And now the only missing part is filling the opcodes. So the first one is 2A. Next one is 26, 36, 2E, and 3E. So now we have the stuff registered, and the only missing thing is implement these two functions whenever we want it. So let's go to after this put register from stack, and let's create rotate left punk. First one is rotates the register, so let's take a register of 8 bits. And the second version rotates a memory, so instead it takes an addressing mode for the memory. Here we go. Now this function works like this. It's very similar to shifting the value. So in the case of the register, we are going to take var value integer equals a p register shifted 1 byte. The new 8 value, like the bit 8, is going to become the carry flag, and the carry flag is going to become the first byte of this new value. So first, let's go for value or equals one if flags.carry.value else 0. So this is the same as saying 1x10 1x00. So basically I am making an arithmetical or setting the byte if the flag is true. Now that I have done that, I can set the C flag value using the 8 member to flags.carry.value is equal to, and let's take a binary number 1 2 3 4 5 6 7 8, but we want the next bit that we are removing, and we are removing it. And value, we want to get rid from that bit, so we are going to make an AND with OXFF, which are the 8 bits maximum value. So what did I do wrong here? Oh right, I forgot to write dot value, because value is an integer and the register is an object. Okay, and now I can say the register equals to the value. Register.value equals to the value. And we have to take 0 and negative flags. So we call our method update 0 and negative flags with a value, and it is going to take that information. So rotate memory is going to be similar, but instead of taking the value from the register, we are going to take it from the address in memory. So let's take from here, let's copy this, and now we have the value from an address instead of from the register, and we just need to shift it 1 bit. So we are working with an 8-bit register, an 8-bit memory, but our integers are 64 bits, so we are cheating a little. So we are getting the memory from the address, shifting, updating the flag, clamping the value, and now instead of setting it on the register, we have to store it on memory. So it goes memory memWrite in the same address that we have written before, and we store the value and update 0 negative flags. So this should be all. Famous last words. So now it's time for what takes the most of our time, which is testing it. So let's see our test scene and find where our row is going to be, which is after full processor. We're going to create a new node. Call it rotate left, create a new script, and locate it in this folder, and its row, create, and we need to clean up this a little. We don't have immediate, instead we have accumulator. The name of the function should be in lowercase, so we are going to change that for all of these. If you are wondering what I am pressing Shift F5 to convert case to lowercase. Now, what do we want from here? We want the accumulator, 0 page X, absolute and absolute X. We don't want any of the last three functions. Thank you very much. And let's start filling up codes. So for the first one, to A, lowercase a. For the second one, 0 page is 26. Next one, 0 page X. 0 page X is 36. Absolute is 2E, and absolute X is 3E. Now let's make some fast addition. Let's add more and more carets to these lines, holding Alt and clicking, holding Ctrl and pressing the right arrow. I will stop at the end and will write rotate underscore left, and that is the function signature and everything. So we'll copy this for the sake of keeping a backup. Comment it. And now let's see, what do we need. So this one only uses the accumulator, it does not use memory, so we can get rid of our template. We can load a number, so we can load it with a binary notation for being more obvious. So we can set some values, 1, 2, 3, 4, 5, 6, 7, 8. So here are 8 bits, and we also want a carry flag for testing purposes, so we can use set carry for this. So we can go to set carry and see that if we execute 38, we are going to set the carry flag. So OX 38. So we are loading the A register with this value, setting the carry flag, and now we can run our shift operation. And now we have to test what is the value that we are getting. Now let's copy this value and let's see how should it have changed. This value should go to the carry flag. So so it will disappear, and the carry flag that is set to true should appear in here, and the carry should be true. This is not false. This is negative because it has a 1 in the last bit, and we don't care of the overflow flag. So let's copy this and paste it and see, give it a shot and see if it runs. And it has failed, and that is because, no, I am looking at the right register. So why did it fail? This is rotate left. Oh, I am missing a number here. So I am missing a digit. So this will become like this. Let's try again. And now it has passed. So roll accumulator, rotate left, pass it. And we can try a couple more cases. Like, how about a case that will no longer be negative, and also the carry flag is not set. So in this case, this will become the carry flag. Let's copy this. This one is going to become the carry flag, and the carry flag that is a 0 will be at the end. And now we are going to have a carry flag. We are not negative anymore, and also not 0. So let's see if this runs. And it failed again. What did I do wrong this time? 1, 2, 3, 4, 1, 2, 3, 4. Okay, carry flag is unset, so this one is a 0 actually. And the one that is in here will become the carry flag, and that is correct. Let's give it a try. And now it has passed, so that is correct. And one more try, that will be only the last bit is going to be a 1, and this should become actually a 0. So 0 is going to be true, and negative is going to be false, and carry flag is going to become true because it is this bit. So let's give it a shot, and it has passed. So yes, we have our test case, and now we only have to re-implement it for the other addressing modes, and we are done. We will be done with this test. So let's copy this. It's a print actually, and paste it here. Let's uncomment some stuff, and we are going to use the 0 page memory addressing, and this value we are going to set it into the memory instead of into the register. So we are going to load 3 memory slots, one for each test. There we go, and we are going to load it into memory 3, 4 and 5. And now we are going to change the execution. So now we are going to shift the memory of the memory and not the register, so we don't need the register, loading the register at all. So let's just delete that. Our opcode is now no longer 2A, it is 26. So let's change that as well. And the 26 opcode with 0 page takes an extra byte for the address that we are going to shift. So in this case, it is going to be 0x3, 0x03, 0x04, and 0x05. So this one we have a 38 in here, which is setting the carry flag, and then we are going to make a rotate left on 0 page with this page. So the carry flag and the memory on this address are going to work together to make the test. So let's update the print and give it a shot. Okay, it has failed, and that is because I am testing the register instead of testing the memory. Memory mem read, and this address was 0x03. This one we are going to read memory 4, and this one we are going to read memory 5. Let's give it a shot, and it has passed. So now we're going to do more of the same. Copy and paste, and the difference here is that it takes an offset from the X register, so we can do a +5 or +6, and we can load a 5 in the X register. So we can go to load X, let's find you, and load X is command A2. So we can use A2 to load a value in A. So we can use OX A2, that is load register X, and a value of OX05, which is the offset we are using in our test. So now instead of 3, we are going to test 8, 9, and 10, or I mean 8. And the same goes to here, +5, +5, and +5. And we also want to change the code of the command that we are running. Now we are going to run 36, which is rotate 0 page, but with the offset of the X register. Forgot to copy this to the other test cases. Now we can give it a shot, I think. Oh, and the name of the print. And this one failed. I did something wrong. Let's see. So I am setting the carry flag. Wait. Did I cut what that was here? Because X is not loaded here. Okay, looks like I accidentally cut it instead of copy it. So second try, and now it passed. So we have roll 0 page X, rotate left, pasted. Now we have to make the absolute version, which is the same, except it has a 2 bytes address memory. So instead of this, we are going to have a 40, 03 or 4 and 04. and we are going to use 2e instead of 26. Wait. Okay, and the memory takes 2 bytes, and because little endianness, you will set first the less significant byte done in here, and here, and here, and then the most significant byte, that is 0x40. Oops. And now I think we can run this and should work famous last words. Okay, it worked. So we have rotate left, absolute. So next one is absolute x, which is the same, except we are going to have an offset. An offset in here. Let's make a +5. And we have to also load the register X with 5. Almost ready for the snake game. Yes, we are too close. We are only missing. This is rotate left. We also have rotate right. A couple of weird functions related to returning from a subroutine. And then transfer register values forward and backward. So this is going to be relatively easy, and I think we can do all of them today and could be ready to start the snake game next stream, and that would be great actually. So here, to complete this test, we need to load the X register with a 5 as we have done before, so we can have this offset and run correctly. And the other thing we need to do is change our instruction to E for 3E and change our print and pass it. Where is my music? So we have absolute X, rotate left. So all the weird cases that I could imagine we could find are covered. We never tried using like negative offsets, and I think it is always signed. So I don't care very much about that case. So let's deal with it. So this is ready to go, and because of that, what we want is our beloved command line status. Let's see what changed. So yes, we registered our roll command. We created functions to handle it. We added the test, and we add the new file for the test. So let's commit, and we implement and create unit test for roll of code. So do we have an issue for this? So this is 36, closes 36, and let's move everything that we want to do today to in progress. Oops, let's make this big for a moment. So I want to do the transfer first. and leave the return from subroutine and from interrupt for the last part, because I don't know how complex they are going to be. I know these ones are easy ones. So git status, this is complete, git push main, no sorry, origin main. So let's create issues for this. Pam, 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 pam. So now we have our roadmap to Snake. So jokes aside, rotate right is the next one. So let's close this and let's tag this as complete. And let's continue with rotate right. So let's move this to the dock. Pam, pam, pam. And we want Godot. Where is Godot? There it is. Let's remove this and let's start working in rotate right. Rotate right takes exactly the same addressing modes. So we are going to make is it in here? Yes. So let's copy these functions for rotate right and let's rename it left to right, and let's see what do we have to change, because now we are rotated in the opposite direction. So first of all we need to set the bit of the value. So let's first take the value from the register without any change, and let's see the byte that we want for the new byte from the carry flag. So value, we're going to use or equals to add bytes, and we are going to use this byte. Bum, ba, bum, bum. So this is 1, 2, 3, 4, 5, 6, 7, 8, the 9th byte. If flags.carry.value, else choose 0. So this part is done. Now we can make the shifting. No, wait, the opposite. I want to now set the C flag to true if the last bit of the value otherwise false. And now we have swapped the value of the carry flag, and we can now choose to do the shifting of the value. So we can say value equals value shifted to the right by 1 bit. We are getting rid of the less significant bit, but we have already moved it to the carry flag in here, and this in theory should never be necessary. So in theory we can get rid of this. We are storing back the value into the register and forget of the rest. So, and for rotating right from the memory, we can overwrite this part for the other part, and in theory this should be all. Not shifting in here, we are shifting down here after the swap of the carry flag, and then write the memory and update 0 and negative flags. So if I am not all crazy, this is complete and correct, but I could be wrong, of course. So let's go to where we have to register roar. So let's copy roll and rename it to roar, and let's make new opcodes for this, and we are going to rotate right instead of left, and the bins are still correct, they are all the same. 1 byte 2 cycles, 2 bytes 5 cycles, I am reading here, 2 bytes 6 cycles, 3 bytes 6 cycles, 3 bytes 7 cycles, so this is all correct. And we are only missing completing the opcodes, which are 6A, 0 page is 66, 0 page X is 76, 6E, and 7E. This should be all for the CPU, and the only thing that is missing is creating a test case. So let's go back to the scene, let's duplicate roll and name it roar, remove this script and create a new one, save it in NES test, and we need to start doing some changes as always. Let's change immediate for accumulator. Let's get rid of absolute and indirect, absolute Y and indirect XY. Let's change this for snake case. Let's make it all underscore. Let's change the function name to add the suffix rotate right. And now we have to add the opcodes again. So here we go. Accumulator is 6A. Oops. 6A. 0 page. Full screen. And 0 page is 66. 0 page X is 76. And absolute is 6E, and absolute X is 7E. So now we have to do the testing. I wonder, can't we copy the cases from roll? Is it a valid case? Like trying to find equitative cases. Let's try it at least with one of them. So here we go, roll, and now if we roll this to the right, and we have the carry flag that is going to become to be first in here, and this 0 will become the carry flag. So carry flag that was true will be set false. This is a negative value because the carry flag was pushed to the last bit and is not a 0. So this looks like a good example. This one is like more of the same, I think. So this one will not have a carry flag. Because we don't have a bit in here. So maybe we should put a bit in here to shift to move, put it on the carry flag. And this is going to move the carry flag to this bit, which was false, and the last one will move to the carry flag, which is true. And now we have a non-negative value and a non-zero value. And lastly, we have a 1 binary number that is going to be shifted to the right. This one is going to become the carry flag, and the carry flag which was 0 will come at the start, and this will become a 0, and 0 will be true, negative will be false, and the carry flag is going to be true. So the part that we are missing is changing the opcode that we are going to run and give it a shot. And we have rotate right in the accumulator working, so that's great. So now we have to repeat the process of before, making the other variants of addressing memory. So let's do that fast. Let's change what is the code that we are running. Let's bring from row the part of populating the memory. Let's take these values to populate the memory. I think we don't need to load the accumulator at all. And now we have to pass the address of where we are going to check for the value to be rotated. So it's 0x03 for the first one, and 4 for the second one, and 5 for the last one. And we also want to change what we are testing here. So instead of the register, we want CPU memory memread. So we want to read 0x03 for the first case, 0x04 for the second case, and 0x05 for the last case. So are we done with this? Okay, so rotate right 0 page seems to be working. That's cool. First try. So let's copy this and paste it in here, and let's add, now it's 0 page X, so let's add an offset to this value. So let's give an, I don't know, 0x12. So from roll I am going to find this case 0 page X. This is the part of the code that is populating the X register, so I will copy it and we'll paste it at the start. but I will populate it with this offset that I want, 0x12. Let's paste it in the other cases, and we also want to change the function that we are going to run and the print that we are going to have, and I think we can already run this. And it failed because I didn't add the offset to the assertion. So once more, and it passes. So wait, let's confirm rotate right 0 page X. So now we are going for absolute, which is the same as 0 page, but takes 2 bytes address. So we are as always going to the 40, 03, 04 and 05, and we are as always using little endianness, so that is putting the 40 after the memory, the less significant byte, and as always changing the code that we're running, and also changing what is the memory that we are reading for our assertion. So if we are not all crazy, I think this is ready to be tested. Here we go, and pass it. So we have rotate absolute, and now we copy it again, and the same as before, let's add an offset in the memory of 0x12. So let's load 12 in the X register for the offset, and let's change the code that we are running and the print. Last one, fingers crossed, and boom, we are done. We have absolute X rotate right. So awesome, that was fast. I am going to start speedrunning making emulator CPUs. Nah, just kidding. Git status, git.import, registered role, created the functions, added the test, and add the new test file, and git commit. Implement and create unit tests for rotate right opcode. Closes 37 if I am not crazy. Yes, 37, rotate right. Push origin main. Oh, git push origin main. Cool. So one less to go. We have rotate right in the back. So I want to skip return from interrupt and return from subroutine, and I want to do these others first, because these two I will probably need to do some research because they work with the stack. So this is transfer stack to X, transfer X to A, transfer X to stack, and transfer Y to A. So we already have transfer stuff. The stack pointer, I may need some research. So we are going to do transfer x to a and y to a first, because they are the easier ones, and maybe we can do them both at the same time. So let's go to our CPU, and this goes to the end. Why is A or why is this at the end? This should be at the start, but no matter. So I will just go after tie. Let's find tie and put transfer x to a in here, and let's see how it works. It takes only one version and takes only 1 byte and 2 cycles. So let's copy this line and let's transfer x to a. So we are going to use transfer register from 2 and transfer from x to a, and update the opcode to 8a. So it is ironically the inverted of this one, but it is a different register. And the other one is transfer ya, if I am not crazy. And let's duplicate this line, and it is the opcode is 98. It transfers y to a. We are going to call it register transfer register from to y to a, and takes 1 byte and 2 cycles, the same as before. And we have this function, so we don't have to do anything else. So transfer x to stack pointer and transfer stack pointer to x. So my stack pointer is not a register, so I cannot just use the transfer register. My stack pointer is just an integer. It is set to reset the stack, which is this value. And I am a little confused of what is the value of this. I don't know if it takes stack pointer or stack pointer plus this, but that would make it 16 bits. So I am betting it is just this. And I think theoretically the other thing is, I don't know if we are transferring the stack pointer, that means the value, or transferring what is inside of the stack. So it says copies the current content of the stack register into X register, but I am not quite sure of what that means. So let's leave that for after we are done with the transfer X and Y, and let's do research after. So we can create we said after tie. What is tie? Tax tie. We can duplicate this and name it transfer XA and transfer YA. Remove the script and create a new one. Transfer X to A, transfer Y to A. Let's see how was it. Yeah, so because this has only one version, we only need 2 tests. So let's copy this as is and let's change it to match our interest now. So this one was loading A and transferring the value. So let's do the opposite. Instead of loading A, let's load X. And to load X, we need, where is load X? Load X. Load X is A2. So we are going to use A2 to load X. And let's transfer that value to A using the right opcode, which is transfer X to A, (8A). So this is 8A. This is TXA. Move X to A. Sorry, because I copied, now I have to fix it. And this one is transfer Y to A. Move Y to A. And the opcode is 98. So let's put it in here. Okay, so to load X we use OA and we load the value and transfer it, and we are transferring in this opcode, and we are going to test the A register instead of X and the 0 and negative flags. And for this case we are also going to try the A register instead of Y, and we are loading Y instead of A, and load Y is, where are you? Load Y. Load Y is A0. So we are going to use A0 to load Y. And we are loading the value and transfer it to A using this opcode and test it and print the result of the test. So let's give it a shot, and it should be at the very bottom, I think. Transfer X to Y to A, passes. Transfer Y to A, passes. And it has worked in the first try. It status add, we have a trailing space that we don't want. Let's clear that trailing space, which is here. And repeat, and now we have this. Git add the new file, and git commit implement and create unit test for the transfer x to a and transfer y to a. Closes. Let's see, it closes x to a is 39. Closes a to a is 41. Git push origin main. Bye bye. So now we have to make transferring stack to x and x to stack. And for that, because I want to know if the stack value is just the position of the stack or the content of the stack, like picking what was the last value, I am going to cheat a little and see an example of how it was implemented. So transfer x to a and y to a is now done, and transfer stack to x is the next thing we are doing, and we are going to check from the tutorial the example of the same code written in Rust, and let's see how they implemented it. So we are going to see the CPU and see how they made the VA of code. So let's find OXVA. XVA, yes, XVA transfer X. So register X equals the stack pointer. So yes, it is the position, not the value. And the other one, transfer X to S, just sets the position of the stack pointer and not the content. So okay, that is actually very easy. So I wonder, how often have I used the stack pointer? Let's see, 1, 2, 3, 4. Okay, so I think I can convert this stack into a register 8 instead of taking the job of writing a new function. Does that make sense though? Just for not writing two functions that takes two new lines, does it make sense to turn it into a register? What to do? So let's see, where is transfer register from to. So let's just write it. It is much easier. So let's do transfer stack to X func transfer stack pointer to register and takes a register as argument, and we are going to say register value equals stack pointer, and that's all. And the other version, transfer x to stack, we're going to do func transfer register to stack pointer. So, and we are going to take the same argument and do the opposite, assign stack pointer equals p register dot value. And in both cases, we want to update 0 and negative flags with whatever we are transferring, right? Yep. And that is exactly what they did here. Okay, so transfer x to s does not update the 0 and negative. Is that correct? Transfer x to x updates, but transfer x to x does not affect the register. So that's a good catch. Setting the stack does not update any flag. And it's kind of time to put it in test, right? So let's see where they are located in the list. So here are my transfer stuff, and transfer x stack to x goes between tie and txa. So between tie and txa in here, we are going to register transfer stack to x. Yes. And between txa and tya, we are going to register transfer x to stack. Okay. So let's duplicate the line here. And this is going to be transfer stack to x, and transfer stack to x, the code is p8. Yes, it takes 1 byte and 2 cycles, and it does. This is transfer. Wait, I will copy it. Do not mistake. Transfer stack pointer to register, and we are transferring to register x. And let's duplicate this line and do the opposite. Transfer it x to s, and transfer x to s is 9a, is uppercase a, and this is transfer register to stack pointer. and it takes 1 byte, 2 cycles. The bin is correct, the function is correct. Okay, it should be all. So let's check it first. So we added 1 transfer stack pointer to register, transfer register to stack pointer, the 2 functions, and seems correct. Okay. So what's next? We are going to make the tests, and we are going to put it next to these 2. Actually, probably, yes, after them. So transfer stack to X and transfer X to stack. Remove this script and create a new one. TSX, TXS, and create. So so we want 1 for TSX and 1 for TXS. They are both immediate, and this is transfer stack pointer to X, transfer X to stack pointer. This is, it was PA, and the second one is 9A. So I think we're more or less ready to start writing the actual test. So let's define this function, and now they both exist, and we just need to try something. So how do I push something into the stack? Let's see. So I think we have a push accumulator into stack, so we can load a 5 and then push it into the stack. Let's see. We have load A and then push A into stack. That is PHA. Where are you? PHA, push accumulator. So push accumulator is 48. So we are going to use OX48 to push this 5 the stack, and then we are going to transfer the stack to the X register with BA, and now the X register should be 5, and 5 is non-zero, is non-negative. We don't care of any of this. And we can do the same case using a negative OB1 Kenobi. And this one, this should be here, and this is negative. And pushing a 0 is kinda useless because 0 is the default. So in order to test pushing a 0, we need to load, it was 0x0009, I think. Oops. Some value that is not 0, 0x33. So we are going to load something into X. Was it A2 for load X? Let me confirm that. Load X is 2A, correct? And we are going to load something, load 0 into A, and transfer, push it to the stack, and transfer the stack to X. So we will overwrite it 33, meaning X should be 0, and 0 should be true, and negative should be false. And this test should pass famous last words. And failed. Why did it fail? What is the X register? If we take a look, register X is 252. Alright, we're transferring not the content, we're transferring the address. Okay. So I was dumb. So we are transferring the address, and because we are transferring the address, I should make CPU dot stack pointer. So this is the test that we want to make, probably. And we don't care of what is the value inside the stack pointer. Let's duplicate the line, and let's say value equals to the stack pointer, this, and pop stack pop 8 should be equal to the value that we want. So let's try that. So it's kind of useless, but the thing is, now the CPU flags will not match because we are using this other value that by default it is negative and non-zero, so it should always be true and false. And none of these matters. And it seems to have passed. Okay, now I am going to copy this and see if I can make it run in the opposite way. So we want to load something, and now it makes sense to load a value into the X register, and transfer it into the stack pointer, and that's the end of the test. Pa-pum, pa-pum. So I want to load a 0 and transfer it to the stack pointer. So the value of x is going to be equal to the stack pointer, and the value of stack pointer, not the pop value, is going to be each of these. And we don't care of 0 and negative flags because they never change. So let's recap. So we never used memory. We forgot to delete this. And so we are loading 5 and pushing x into the stack pointer. They should be the same, and stack pointer should be 5. Loading this binary number and pushing to the stack pointer. They should be the same, and they should be this binary number. Pushing 0 to the x register and setting it to the stack pointer, and they should be all equal to 0. And this sounds like a good test case, and has passed as well. So we are good to go. That was pretty awesome. Git add status, yes. Git commit, and implement and create unit test. Oops, this is lowercase, this is uppercase. For transfer x to s to x and transfer x to s. Closes. Let's see, what does it close? 38 and 40. Closes 38. Closes 40. Git push origin main. So done we are with these two bad boys. So look at this. We are so close to have the full set of the 6502 CPU. So we only are missing return from interrupt and return from subroutine. So return from the problem with this is that it is a little weird. So return from interrupt instruction is used at the end of an interrupt processing routine. It pulls the processor flags from the stack, followed by the program counter. So the thing is, it pulls the P register, that means the flags, and then pulls 16 bytes, 2 bytes, 16 bits from the stack for the program counter. So let's check that, and let's see. After rotate right, let's add return from interrupt. So let's put that in test. Next CPU. After rotate right here, let's put return from interrupt. Let's duplicate the line. It's RTI, right? RTI, yes. And let's say return from interrupt. and takes no binding at all. And the opcode is 40. It takes 1 byte and 6 cycles. It makes sense. It takes a lot of cycles because it copies a lot of values. And now we need return from interrupt function. I will put it after rotate right. Return from interrupt. Func return from interrupt. And what this does is pulls the flags, so that is flags.value equals pop stack pop 8. So the stack is 8 bits and flags are 8 bits, and then the program counter, so that is program counter equals stack pop 16. Program counter are 2 bytes, and I think this should be -1 if not crazy. Right, this is program counter.value because it's a register. And let me confirm this. Followed by the program counter. Do I have to subtract 1 or not? Let's see how it works in the Rust example. I am pretty much convinced, according to what I am reading, that I do not have to subtract. But let's try 0x40, and it sets the bits of the status from the stack. Status remove break and insert break 2. What is that? It seems to be flipping 2 flags, so I am not sure which are break and break 2. We are going to find out pretty much soon. And then sets the program counter and does not subtract, so that clears it. So let's find out what is this. The RTI instruction is used at the end of the interrupt processing subroutine. It pulls the processor flags from the stack, followed by the program counter. So it does not say interrupt disable is set from the stack, so we don't have any flag in here. So what is this break and break 2? Let's find out. So we have 0, 1. So we have carry 0, interrupt disable, decimal, break command 2, overflow, and negative. So it is the 2 that we never used. So it is unsetting the 5th bit 0, 1, 2, 3, 4. And how did I call it in here? 0, 1, 2, 3, 4. 4 is B for break, and we don't have 5, so we can make B2 for the 5 and flip them. So it's return from interrupt. Okay, So we are going to flags.p, we unset it, and flags p2 value, we are going to set it. Is this correct? Gray I choose. So remove, insert. So there is information about these flags that is not mentioned in the reference of some commands. But there is in here a comment of why this happens. Let's see what is this URL. So we have interrupt, no CPU effects, see the B flag. The B flag, while there are only 6 flags in the processor state register within the CPU, the value pushed to the stack has 2 additional bits. Though these do not represent a register that can hold a value, but can be used to distinguish how the flags were pushed. The bit 5 is always pushed as a 1. Bit 4 is called the B flag and represents a signal in the CPU controlling whether or not it was processing an interrupt when the flags were pushed. Interrupts ERQ and NMI. Push a value with 4 bits cleared to 0, instruction PHP, and break push the value with the bit 4 set to 1. The B flag is not conventionally called part of the processor status register. This is because it represents a transient state, not a state that persists from one instruction to another. The CPU pushes a value with B clear during an interrupt, and pushes a value with B set in response to PHP or break, and disregards bits 5 and 4 when reading flags from the stack in PLP or RDI instruction. What? So basically, whenever we push the value, we need to set these values to this before pushing, and don't change that when pulling. That is what I am taking from here. So is this what is happening in here? So this one is pushing the processor. No, this one is pulling the processor. So why is it changing it after the pull? That doesn't sound right. Right, interrupt is set to 1, interrupt is set to 1, interrupt is set to 1. Well, it's interrupt disabled, not interrupt. Interrupt disabled. When set, all interrupts except the NMI are inhibited. can be set or cleared directly with save clause, automatically set by the CPU when IRQ is triggered and restored to its previous state by RTI. If the RTI line is low, ERQ pending, when this flag is cleared, an interrupt will immediately be triggered. Okay, so I don't know what this backslash refers to, but it looks like I am under the impression that this code is incorrect, because this is affecting the status on pull and it should be affected right before push. So I am going to do that. I am going to take these cases, these 4 cases, and set the values before pushing and never change them in any other moment. So we don't take this, we don't change it in here, we change it in push processor, PHP, and before pushing the register, we're going to say if B register is NES register flags, we are going to set both to true. That is the right thing to do. Right, so we did not implement break properly, probably. So let's see this other IRQ, and we don't have IRQ in our table. Nor we have NMI. And why is that? What is IRQ? Interrupt request is a signal on the NES CPU. It is used to trigger a CPU interrupt if the CPU's IRQ input is 0. So I guess that backslash is what IRQ means. If the input is 0 at the end of the instruction, then the CPU pushes the program counter and processor register to ignore further ERQs, and the program counter takes the read value, read at this and this. Okay, so I am assuming we are going to talk of this later, and we only need to care about pushing and break. So what does it say of break? Break ERK force interrupt. The break command is set to 1. The break instructions forces the generation of an interrupt request. The program counter and processor status are pushed on the stack. Then the IRQ interrupt vector blah 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 is loaded into the PC counter, the program counter, and the break flag in the status is set to 1. So basically, the interpretation of a break depends on the operating system. On the BBC microcomputer, it is used by language ROMs to signal runtime errors but it could be used for other purposes. So that means in the case of our NES CPU, we have to do what we have to do this. So it's like we set the flag and push the processor flags and the program counter, and then change the program counter to whatever is stored in these two memory addresses. So let's see that. What does break do? So we don't even have break in here, and that is because we made break into the parent class. So let's rename quit to break. Oh, I cannot name it break. Okay, CPU break, and let's rename quit to CPU break. And let's rename CPU break for something else. So the problem is that if we do that, we can no longer use break to end execution of programs. So tags the NES CPU, and now we can override break. Reset load run, get operand address. Okay, first one in the list. Wait a second. No, we are passing a callback. Now I am concerned. So I can override the break in here. So yes, we can keep quit in the base CPU as it was. And copy this. Go into our NES CPU, paste it, so for now we are going to create the function NES break, and let's create this function. Yes. So NES break. Conk NES break. And we are going to do what this requests. So we are going to set the break flags break value equals true. Wait, p equals to false. Flags p value to p2 value equals to true. Is this correct? According to this documentation. Bum, bum, bum. So I was looking at this web page. And this says in break, oh, both are set to 1 in both PHP and break. So that sounds about right. So both are set to true. Then it says forces the generation of an interrupt request. The program counter and process status are pushed on the stack, and it's in that order, right? So let's see what break does in here. Really? It does not even say break. 0x00. Oh, it just returns. It does nothing of what the other thing says. So I am a little concerned about that. So the thing is, this is about the 6502. Maybe the NES does not do this, but it says it does in here. Well, there are only 6 blah 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 blah. This do not represent the flip flag. So all I want to know is what is the order. So if return from interrupt, it is pulling the processor and then the program counter. Then that means I need to push the program counter and then the processor. Okay. So stack push. Why it does not show anything? Oh, am I missing a comma or something? Yes. Stack push 16, and we are pushing program counter value, and then stack push 8, and we are going to push the flags. And then we are going to go quit for now, which is the parent quit that we was having before. So I don't know what is going to happen. In the future, but for now we are going to push and set the stuff and then stop running. So we are going to set is running into false, and this should not, the loop should not run anymore. And maybe the new something in the future will set is running to true again, and this is going to be restored and continue running. So I think setting is running to false is correct behavior, because it kind of pauses, and then the return from interrupt will reload this, and then set is running to true. So I think return from interrupt should pop these values, and then says is running equals true. Probably. But I will not test this because I have no idea how to test this. Music. So what do we have? Git status. Git this. So we registered break. We are overriding previous break. And we registered return from interrupt. We have the new NES break. And we are setting the flags that we was missing on push register. And we are returning the flags on the program counter from the stack and setting running to true. So maybe instead of calling quit, we should call is running equals false for readability and consistent, because we don't want to maybe change the behavior of quit in the parent class. So I am pretty much sure this is correct. So now every time we call break, we should be able to pop the flags and the program counter from the stack. So maybe we can do that. I will leave it as is for now and hope it makes some sense in the future. So git add. So we implemented break and RTI. Commit implemented RTI and NES BRK opcodes. No unit test. Closes. Let's see, what does it close? Okay, RTI. And let's edit it first. Implementation, no unit test for RTI and break. So convert to issue, link to project. Okay. Closes 42. And now we need to implement git push origin main. And now we have to implement real-time strategy. So what is RTS? Maybe we also cannot do unit test for it, because if it deals with interrupt, it's going to be a little difficult. So the RTS instruction is used at the end of a subroutine to return to the calling routine. It pulls the program counter -1 from the stack. Processor status after use. So it only pulls the program counter -1. So it's stupidly easy to make. And it goes after RTI. Pum 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 pum. So we are going to open our NES CPU. Let's search RTI, and we are going to make return RTS. Yes. Opcode new, and let's see what is it. What is it like? Let's close some stuff. So opcode return from subroutine is 60. Sorry, OX60. RTS. Wait a second. Now that I think of it, well, it's more or less safe. But I realized that this one is missing the ampersand. Anyway, so RTS takes 1 byte, 6 cycles, and it will go return from subroutine. Routine or routine. Okay. And let's implement that. RTS return from subroutine, and it is a program counter pop16. And according to this, that is all. Now this one does the -1. Let's check on that. So if I look at the code sample, what does OX60 do? So it is actually +1. So jump to subroutine will push program counter +1, so it's +2 -1, and then this one makes it +1. Oh, because it also needs to advance, because it will not advance because I changed the program counter. So that makes sense. So that is all. Famous last word. I will also not test this. It's too difficult and the function is so simple to mess it up. So let's go to git status, git add. Let's add only this. Git commit amend. And so we put that change in the previous commit. Git add this. We add return from subroutine with 60. Git commit and implement return from subroutine opcode closes. What was it? 42? Oh, we never created it. 43. And now we have to push it with force because we amended. So we are free, we are done, we have all the CPU finished. That is extraordinary, guys. This is the end of the stream. We have finally finished our CPU and we are ready to start making our Snake game using our emulated 6502 CPU. So thank you very much for watching. See you next every Saturday and Wednesday as always at the usual time, 9:30 Argentina. I have no idea of other countries. And thanks.